And we finished last time 2 weeks ago on this moment. Okay, do you see this presentation? Yes? No?
Yes.
Yes, okay. So, assuming building a model is the first step in a system science attempt, because we work only on models. We experiment on models by simulation, investigation. We check everything we want to just using model. So having a model is a crucial problem of this system theory attempt. The best model which we can get is the model we derive from precise description of the system. Like in this electrical circuit I have presented on the first class, the first lecture. We have full total information about rules, about equations, and we used them just to derive the model. This model, in fact, is some kind of dependency between what we want to name as output and what we know to name as input. It is, let's say, simple. It is also simple because we try to deal only with linear systems. What means that we can use just linear algebra algorithms, methods, and this method in multidimensional case are very say useful, very easy to maintain, very easy to use just. And even the problem is big. I mean, we have very big number of inputs and very big number of outputs. Anyway, we deal with the matrix. And we deal with such problem as multiplying matrix one by one, or with the problem of finding the inverse of matrix. These problems are solved, and we have, let's say, ready to go packets of program to use. But sometimes we have no such complete knowledge. Maybe we could have such knowledge, but following this knowledge, the model would be not easy to operate and maybe too complicated to use it because we always try to find the model as simple as it possible is. And you take a look at the second point of this slide. So about what is this voltage divider? What is an example? What for is this an example? In my opinion, it's a very, let's say, very wise example, because we teach from this example that even for very simple equipment, for very simple device, for very simple problem, we make assumption in which we try not to take into account some value, we try to omit something, we try to assume certain properties in order to get the model simpler. And coming to this voltage divider, what is about? Okay, momento. Maybe this whiteboard. Go. Okej, współpracuj. Wszyscy możecie edytować, ale nie ruszajcie po cichutku. Okej. Moment. What is voltage divider? I hope everyone knows this. We have two resistors. And we would like to form voltage which is desired for example, supplying transistor and this transistor we can imagine can be connected here, I mean here, later on. And for for transistor, we need to provide electric energy. We need to supply this energy to this transistor, and we need to formulate normal point of work of this transistor on its characteristic, on its static characteristic. So before we start to use this transistor, anyway, we need to set this, I don't know, nominal point of work for this transistor. It means that we need current voltage to do it. And we should put precise voltage to every point of electronic circuit we use. And these points differ with each other. I mean, for a certain part we need, let's say, voltage 9 volts. For another parts of this electrical complicated circuit, we need voltage 6 volts, and so on and so on. And as of course you know that our battery or supplier has the set voltage value. We do not have, for, let's say, for our cell phone, two battery, one for one part of this, the second bigger or higher, with bigger, higher or lower voltage for another part. No, it's only one battery. So it means that there exists at the beginning only one voltage. So we need to supply different values. So we use such simple devices. Billions of billions in the world, such divider we can find in billions of equipment, electronic equipments, everywhere. Even you and me, we have now plenty of such voltage divider to our disposal. So it is very popular. I take a risk, and I would say that the most popular electric part of a circuit is a voltage divider. So How it works? Of course, you know that we have here voltage U1. U means here voltage as in original domain, electrical domain. Here is the voltage U2, U2. Był ktoś na koncercie U2? Have everybody have someone of you been on the concert of U2? Zaraz się zapytacie, co to jest U2, no i wtedy ja już chyba wybuchnę. Czy wiecie, co to jest U2? No
yes, sir, we watch YouTube.
Proszę? Please? I try to,
Yes, we know
to stimulate you, to encourage you to say something, because it's, let's say, very stressing when I'm talking to my screen. There are no students in the room. I cannot take a look in someone's eyes, and I cannot try to say something personally. So it's not my kind of behavior. Just be cold and not seeing students and so on, and speaking, and thank you, goodbye. No, I try to have a contact with young people. It's very important for me. Anyway, U2, and I have seen a film about Luciano Pavarotti. I hope you know who it was. And Luciano Pavarotti has invited Bono to special concert to Modena, charity concert. And it was very special because Luciano Pavarotti just called Bono and said to him, I would like to invite you to the concert which I organize for charity purposes in Modena, let's say in 2 months' time. Please decide now, and I come to you to talk about it. And Bono respond that okay, maestro, okay, but I'm in Ireland. No problem, said Pavarotti. We are just at your doors, at your home. So in 3 or 5 minutes they were talking about this problem, and of course Bono accepted this invitation and give a performance during this event. Have you heard this or not?
We haven't. I mean, I haven't.
Okay. So it's some kind of ciekawostka, jak mówimy ciekawostka? Zna ktoś takie słowo? Nie znacie? No ja też nie. Okay, so let's go on. Of course, everybody knows that we write just like this. That the voltage at the beginning is divided into 2 parts. The second part, U2, is as we desired. It means we should choose proper values of these resistors. How to derive it? It's rather simply, but just see one fundamental assumption. We assume that this voltage divider is not biased. biased, not obciążony. No, there is nothing connected to this points. Nie wiem, jak są zaciski.
Terminals.
Jak?
Można powiedzieć terminals.
Terminals. Okay, dziękuję. Terminals. So nothing is connected to. Nothing. In this case, of course, this relation, this equation is true, because this current is flowing through this resistor, so it is obvious, so it is true. And we can put just exact, that is equal. But we do not take or build this voltage divider, and next we do not not connect anything to it. In opposite way, or of course we use it to supply voltage to certain point, to certain device, which is here. And in this moment, this relation is anyway precise. Of course, we can just write like that. So we can say something that, but in projecting of such voltage divider, we take into account only this parameter. We do not take into account this equipment, which will be connect later on to this voltage divider, which will be supplied by this voltage divider. No, we do not take into account because this equipment can be could be of different size, of different kind. What is common for electronic equipment devices? So-called input impedance. Impedance is something more than resistance. Okay. Someone of you know what is impedance?
We had that in other lectures.
Mieliście to, tak?
Yes.
Okay, so of course, and the electronic devices are usually constructed in that way that this input impedance is very, very, very big. I mean, mega ohms and so on. So in this case, of course, we can assume that this is almost equal. Anyway, it isn't, because on let's say 5 place after point dot, it is not true. But for engineer purpose, it is true. So we can use this formula to project to choose this voltage divider. But from the systems theory point of view, we obtain this description applying some simplifying assumption. And it is typical for building a model which we cannot just derive from precise equation, from precise starting equations. We just take some simplification, and we agree that our model is not 100% good, but let's say if it would be 90-95%, it is nice, it is okay. For engineer purposes, it will work properly. So it is the second let's say, method of deriving model. The first one, I remind you that was exact model. This one is model in building in building of this model, we did some simplification, some simplification, some assumption, some simplification. We omit influence of certain factors. For example, when I try to model the temperature inside of this room, my room, and I have heating devices, I can tell that the temperature outside of my house has no influence for this temperature, and I just consider heating devices, amount of air in this room, the surface of windows, and so on and so on. But I assume that the temperature outside has no influence. It is true? No. But in that way, I can find such model, because I simplified this problem. I can find a relation and derive the model. In opposite case, it's impossible, because this model become to be more and more complicated, and I could allow for having very complicated model, but this model will serve later on to derive, for example, control algorithms. And I know that if my model will be more complicated, that means that in the future, when I try to find control algorithms, these control algorithms, which will be calculating, taking into account this model, will be also much more complicated and maybe not possible to realize, to apply, or not to derive, for example. Having this in mind, I know that I must simplify my model as possible as it is, in order to get relation in which not all, but almost all behavior of my system will be explained. Have you understood? No. Okay.
Yes, we did.
Yes. Thanks. So I'm joking in such a way that I tell my colleagues when they ask me about reaction of students during lecture. For example, if they understand what you say, I tell them always that I have very good relation with students. They understand quite well what I'm saying. Why? How do you know it? Because we at the beginning have an agreement in which we said that if I ask if something is wrong, or if something is not understandable, or if something is good presented, the students, when it is good, when it would be good, the students shouldn't say anything. So the silence means that everything is very, 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 very well. And when I ask you for something, you do not answer. It means that everything is very, very fine, very, very well explained, and so on. Do you understand this kind of joke? Zrozumieliście coś z tego?
Tak.
No właśnie. Proszę. Nie wiem, czy obcokrajowcy zrozumieli. For example, Carmen, have you understand this joke, kind of joke, Polish joke? Irony or something like this?
Yes, everything is okay.
Okay, thanks. Okay, pobierz listę obecności. Okay, so let's go on. And now this, I hope, explained the main idea. Widzicie teraz, do you see this presentation now?
Yes.
Yes.
And when we do not have these two first possibilities, it is impossible. We have no relation. Such relation for example, does not exist. Nobody has investigated before this problem. I googled it. I cannot find anything about it. For example, for my special kind of system. So it means very, very terrifying things. I must do something on my own. I must do think it over and find solution. But I live on my own. Mr. Google do not want to cooperate with me. I cannot find anything. It's terrifying for today's people, because everybody is used to just get a ready solution from Google, and okay, and after that everybody report very report that I have solved this problem. What? How do you solve? How have you solved this problem? And how? Normal. It means I turn on the computer, shut on the browser, I wrote Google, then I wrote a special request, demand, and I get an answer, then I copy it, and it's solved. Normal. So, but it is in fact not solving a problem. It's just monkey copying knowledge. In my opinion, it is very, very bad. That is possible in everything, because it makes people being lazy. It means almost nobody not think it over. How what is the solution? How it was derived? What are the properties, and so on and so on. Just take it and apply it without with confidence, total confidence that is correct. Why is correct? Because I found it in Google. No, it's not a way of thinking for scientists, but it's a pity that we observe also in science such kind of reasoning. So, and now the third problem. When we do not have this information, this formal information, we just can make experiment. We can observe a certain system. We can observe a certain system, or we even can maintain with the system. We can experiment with the system. It means that we can just choose our inputs and put it to the system and just measure, observe the outputs. After collecting this data, we think what to do, how to derive the model from this experimental data. We realized that in this case our models wouldn't be 100% exact. It is impossible. It is impossible, because the knowledge which we get from the reality is noisy. for example, the data, let's say, are not repeatable. For example, I put certain value to the input, and I note that on the output is certain value. I put the same value on the input once again, and I realize that on the output it is little bit different value. So it is not repeatable. Why? Because on the output have always influence the disturbances, the noises, and the noises are changing, for example, randomly. So in the second moment, the values of these noises were different than for the first time, and so on. And of course, such model. Someone could ask, what for this model which is not good? No, this model is good, but it is not 100% exact. And I ask in return, just like that, what do you want to have or to know? Nothing or partial knowledge about this problem? I hope you agree that even partial knowledge about this problem is better than have no knowledge about it. It's obvious for me, for example. So that is why identification procedure are applied to find the model. And I now leave this procedure of identification because I would like to continue the work with the model, and I will go back to this problem later on, because when we would have only lecture, it is not problem, but having parallel exercises, I must think what to do on these exercises and to have one, let's say, one way, one by one, not going left or right from the main path. So I skip it on, and I, for example, on the next meeting I will to zaznaczę, poczekajcie. I will go back to this slide. Nowy slide. Dobra, poczekajcie. Muszę to sorry for a moment. I must put a note to this point of presentation in order not to forget what I said. So okay. Now I can imagine that you do not see anything. I mean, you do not see this presentation.
We see.
We do.
You do. Okay. I thought that if I do something, it disappears. Okay, so I left it for the next meeting. Okay. Slide. Okay. Okay. And maybe this. Now we will consider so-called aggregation problem. And we start with such statement that in fact systems are built of elements of subsystems. So it means that when we say system, we have in mind rather something complicated, rather something which consists of plenty elements, or plenty, for example, maybe subsystems. So we think that such system has its own structure, own goal for which the system is built. And having this in mind, now we will try to describe this whole system, starting from beginning, I mean starting from its structure, and we think it over what we can do later with this structure, what we need for our purposes and how to do it. So structure, of course, we have elements, and for example the elements could be of types you can see on this slide. I mean that there are systems multidimensional, which elements are multidimensional subsystem or elements. The number of inputs and outputs you can see just on this slide. Okay, and how we can connect these elements, these substructures, subsystems. Let's focus on elements first. I mean that now we will try to connect elements in order to obtain a system. And as you can see, we have, let's say, 3 types of connections. The first one, cascade, series, the second, parallel, and so-called connection with feedback. Oh, when we apply all these 3, we just get mixed structure. And example of series connection is obvious, but you can see that element E1 is an element of 2 inputs and 2 outputs, as you can see. And element E2 has corresponding 2 input and 1 output. And the most important thing is that every output of E1 is connected to corresponding input of E2. For example, do you see this pointer? Widzicie to?
Yes.
For example, when the system E or subsystem or element, anyway, would have three in outputs, and for example, the structure would look like that. Moment. I mean that the third output of E1 would be connected to the or taken as second input of E3, and now we do not consider such possibility because in this case you can see on the screen, we can straightforward apply matrix description in order to achieve final model. If would exist such situation as I said before a minute ago, it would be impossible to apply just matrix calculus, and we should apply just a single equation and the system of single equation, which of course will be much more complicated to operate with. So, as I said, we do not consider such connections. It means when two objects are connected, it means that every output of one object is connected to the corresponding input of the next one, and the number of input and output is the same. So in this series structure, the signal is going through all of elements, and of course, when one of this element is not good, it means that the whole system works bad. And the most simple case is when we deal with so-called seesaw elements or system. I mean the systems or elements in which we have only one input and one output. And in that case, we can just see this connection as at the bottom of this slide. The next structure is parallel. It means that the signals, the same signals are put for inputs of two or more elements, and the output of these elements is summing. In this figure, you can see that we have two elements. Each of them has two inputs and one output, and these inputs are put to these elements, and output is summed by summing junction, as you can see on this slide. And of course, in this structure, it could be considered also for seesaw elements. And the solution would, like you can see here. Please take into account that this system of description is the same, exactly the same, as it was proposed for certain element. We use the same notation, we use the same ideas of signal flowing, and so on. And of course, we can apply two methods of finding negative values. One of this method is presented here. It means that by this summing junction, we write minus. It means that this signal, in fact, is subtract, dziękuję. Subtract from the sum of the rest of signals. Or we can just write here minus, but I propose to do this notation because of next connection. Moment. So in parallel structure, signal is going through all systems simultaneously. Of course, it will work even one or more element is out of order. So here is the here you can see the structure with feedback, and because of this structure in which we put minus here, which denote negative feedback, it is for me better that we will denote all parts of negative signal with minus, putting this minus here by the summing junction, because it will be clearer to let's say to describe, to see, to observe, to imagine whole system, observing where we have minus or plus. Especially it is very important in this feedback structure. What is this feedback? You can see that feedback means, as you can see, that we have, let's say, basic element, E1, basic element, and from the output of this element, we take this signal and put once again to the input of this system element E1, and in this case we have negative feedback, so this signal is subtracted from total input from these input signals. What for? This structure is very important structure because this structure modifies properties of this element. We can obtain different modification applying different kind of this feedback. First of all, second, every control system works on the similar way, not on the exactly the same, but on the similar way. We can say it. What next? For example, when we would like to build a PhD regulator, maybe some of you know what is PhD regulator. I will tell you about it. Maybe on the last lecture. We have certain element E1, and we apply proper chosen negative feedback, and we modify this characteristic of this element E1 in order to obtain the properties which we desired. Sometimes when the properties of this element are not good, especially in dynamic cases. So, for example, the properties of this element this system works nearly on the border of stability. Applying certain correction, we can shift this point of instability, and this element will work, let's say, safer. Zrozumieliście?
Can you repeat once again, please?
When, for example, the properties, in a dynamic case, in dynamic case, we should work with systems which are stable. It means because when system is not stable, then it can be damaged as itself because it's not stable, for example, just simplifying. And when we have certain element, this element is as it is. We cannot just change something inside, because this element is as it is. But applying this negative feedback, we can modify its properties in order to get properties desired for our purposes. Maybe this.
Yes.
No. Different example of system with feedback would be, for example, a room heater. which have
Heater,
set temperature.
heater, you mean this taki calorifer, tak? No,
I mean,
no.
with temperature control, so it's aims for one temperature.
But
With thermostat.
moment. We modify properties of the system, not of the controller. It's a difference, you know, because system is as it is, and we cannot change. We cannot access to inside of the system and to repair something, or let's say to do something. But we can modify its properties applying this feedback. Maybe later on, because in the case when we calculate something, it will be obvious. For example, we can, if for example, we can do this. If this element E1 has such property that for increasing U2, this output is decreasing. And for example, for us, it is not good, not proper, but this system is as it is. So applying proper feedback, we can change it, because final coefficient will be positive, so it means that in fact this value will have a positive influence of this output. You understand? We can change it, we can modify, because it is changing. No, wszystko się zmienia now. Changing, it is changing. When we will calculate something, it would be maybe better understandable. Okay, and this type of feedback can be positive or negative, but in general we use negative feedback. The negative feedback is something. Negative feedback in general stabilize the work of the system. Negative feedback we can imagine when in the classroom the teacher try to say something to the people, but they talking with each other, and when the teacher is try to speak louder, of course the listener, the people, also try to speak louder because teacher disturbed them. So it is some example of positive feedback, because teacher hearing the noise which is bigger start to speak louder, and so on and so on and so on. Of course, it must crash in a certain moment, because let's say the teacher cannot take it anymore and just say shut, and so on and so on. And the negative feedback, the system work in opposite direction. So, for example, imagine what I'm saying is very interesting, but you are anyway talking with your colleagues and so on and so on. Me hearing that we are talking, I'm starting to speak leiser, and you are interesting in my speech, and you do not hear now because I'm starting to speak leiser. So you just try to moderate this noise. It means negative feedback. Rozumieliście? Understand?
Yes.
Okay. I ask you if you understand, boys. As usually you can observe in the film about army, because sergeant who has the rank of boys, of course, usually speak very loud and understand. Yes, sir. Very, very funny. Okay. Okay. And for example, this mixed structure can be, as you can see on this slide, we have this serial connection or parallel connection and this feedback connection. And the problem is that we would like to describe this whole system as one equivalent mathematical, I stress it, description. Why? It is very important from 3 points of view. First of all, when I would ask you about property or properties of this system, in general, when we deal with static systems, it is rather simple task, because I would say that this system will behave as a certain static element of a certain amplifying coefficient. That's it. But if we will deal with dynamic elements of different properties, seeing such structure and knowing what is the description of each element, I cannot say what will be the behavior of the whole system. I must aggregate these elements into the form of one equivalent mathematical element. Then, studying these properties of this mathematical element, I can tell you what will be behavior of my system. Of course, having only mathematical description, not using a real system, not experimenting with real system. And this now will be the purpose of our lecture: how to find the equivalent description of whole system in the form of one element. It is just aggregation. It's aggregation. I repeat once again, we do not build new element from existing elements, as you can find in internet, for example. We just do it in our mind, let's say. So it means we just build a model of equivalent element. Model. Physical such element maybe does not exist. We cannot, let's say, just build it with tools, mechanical tools, or whatever. We cannot just, but we can find mathematical representation. So the main idea is good, because anyway, we work here in systems theory on mathematical representation. It would be nice. Okay, very well. So how to do it? You can see here just a certain example, and this example is wrong. What is the wrong part of this element? I will change later on. I muszę to zmienić. If something...
There are two outputs on the left.
Exactly. We should add... Ja myślałem, że tu mam zresztą, szczerze mówiąc. I have presentation with this change and presentation without this change. So I must check it precisely, carefully. So here we should have two outputs. So it means that this structure is of real elements connected, as you can see here, is changed into one model with one input and two outputs, because here we have two outputs. And aggregation means the procedure from the left to the right. And sometimes we need or do the inverse procedure, so-called decompositions, because when we aggregate our elements into one mathematical representation, then we calculate something using this aggregated model, but we can say only something about the relation between these outputs and this input. And we, for example, just can say what will be response for certain input equal 5. 5. You know, now we have input output, so value 5 means without any measure, because it is just signal. We left this measure in the first stage of systems theory attempt, changing real values into values of systems theory. I mean inputs and outputs. And what is going inside? In this case, I don't know. So, using this aggregated model and calculating what we need about these problems later on, we have no knowledge what is going inside. For example, here, we haven't such knowledge. When this knowledge is important, we must go back to our formulation, background formulation after decomposition, and to, for example, find this value, the value of signal inside, because, for example, we know that in this point we have limitation for the signal. Because the signal cannot exceed value, let's say 10, because it's dangerous for the system. It can damage the system when here occur the value 12, for example. So after calculating and after finding control, for example, we must check if everything would be okay in a real system. And that is why sometimes we need decomposition, especially when there exist limitation inside of in our systems, in our system. Sorry. Okay. In general, the formulation of aggregation you can see just here. It means we have structure of our system. We have models of every element, and of course we assume that our models are linear. As I said, it would be possible, this kind of work, I mean aggregation, is possible only for linear objects, because for non-linear object we sometimes cannot calculate. We cannot, let's say, solve equation square of higher order than square. So everything I do, everything I do it for you, tak? Who sings this song? Someone of you knows?
No.
I know the song, but not the singer.
Bryan Adams śpiewał. Bryan Adams. Znacie takiego. You know Bryan Adams? Very old guy. In my age, maybe. Okay. No. I think maybe not so old. Okay. But Bryan Adams. Everything I do it for you. Okay, so me too, and for you. So we deal with linear models only, and this aggregation algorithms means finding the relation. You can see just here relation in which we should find certain function of multi-dimensional background. So it is just, let's say, formally description of the goal of this aggregation procedure, to find final dependency between every models and total whole aggregated model. And if we deal with structures which are connected parallel, true, in serial, the final description can be calculated according to this formula, in which we should multiply the matrix from left to right side, but we should multiply them in backwards way. Why? Maybe why? And in the structure parallel, of course, summing. And in the structure with feedback, we have such expression. When here is identity matrix, I mean a matrix with only one on the main main diagonal, and zeros on other places. When for negative feedback, we have here plus, and for positive, minus. Okay, so. Dobra. Która to godzina jest? Okay. To tu coś chce. So now I show you why this formula existing and why they are correct. Maybe on this whiteboard. I try to open whiteboard. Maybe you can see the screen with this circle.
We can, yes.
Can see it.
Один, два, три.
We can see the whiteboard.
You can see this blue line going around certain circle.
No, I
No?
don't.
We can see only red circle.
Now I can see only. So maybe not this.
Can you try to disable the whiteboard and start it again? Because sometimes Teams like loses track of the whiteboard.
Maybe.
If you could try to stop.
But okay, but you know, I do it here. Maybe it would be better. Okay, do you see paint screen?
Yes, we do.
Yes.
Maybe better. So we can imagine, for example, two elements which in fact are multidimensional, I have drawn this arrow, this certain kind of arrow. This kind of arrow for sure means that we deal with multidimensional signal. But every time I say something about but, prawie but mówię, może nawet źle wymawiam, bo to tato jest takim Anglikiem, że to odróżni. No czekaj. No bo but to też coś innego znaczy, nie? To
Nie
wiecie. Proszę?
Nietoperz.
Nie to pewnie, ale jeszcze coś innego znaczy. To
Kij.
jest,
Jak pałka do baseballa to jest bat.
ale jeszcze to znaczy chyba tyłek, moim zdaniem, nie?
A, no
Tak.
No, lub jakby kto by to chciał inaczej tłumaczyć. No właśnie, no to jest taka kwestia, jaka jest, tak? Co by to? Anglikami nie jesteśmy. Okay, I mean that even if I draw an arrow, just simply arrow, and later on I put here a big letter, for example, G, czekaj, letter, according to from G1, and here G2, when I put inside of this square in the block, in the
Yes.
square, okay, dziękuję, thank you. When I put this big letter, it means that this and that signals are multidimensional, because here we can see big letter which denote matrix. So let's do it here. How to derive this formula? Of course, here we have the input u, and here we have the output y. Because these elements are connected with each other, we should denote this value which is inside of this system by certain letter. For example, I will denote always these inside values by W. W with index when there are more than one inside values. But in this case, I mean more than one, in this sense that there are 2 points in which I should denote this value. It is something different from that fact that all of these values are vectors. Anyway, this value W is vector. Is vector of, for example, three features. Ja, żeż ty. Tu potrzebowałbym indeksy, a tego znowu nie pamiętam, jak to było. No dobra. WA. So, for example, I must have in mind that every value I can see on this figure, u, w, y, in fact, they are vectors of different number of features. What is the number of this feature? A is good, correspondingly good. I mean that all outputs of G1 are connected to the corresponding inputs of G2. And how to describe this system? First of all, I can write relation for the first object G1. It means that the output, in this case W, is equal G1 multiply by U. And the second equation, of course, Y equal G2 multiply by W. And I will show you now. Okay, when I'm writing, you cannot see anything, but yes, here it is. Okay, because they are connected, I put in mathematics this symbol, which means systems of equation. These equations are vector matrix equation. And I can solve it by substitute this value which are not needed in final description and applying substitution one by one, and so on. I can find relation. And you can see that Y is equal G2 G multiplied by W. In the place of W, I take the relation from the first equation and put G1 multiplied by U. And it means that final description is this, that the multiplying of the matrices is in the backward way. So when the matrix is coming from left to the right side, multiplying is in the opposite direction. So final description is in the form of certain matrix, which parameters can be calculated according to this formula. So it means I can treat whole system as one corresponding system as you can see. Okay. It will be clear. Okay. Okay. So just like that. So it means that I can treat the system of two elements, multidimensional elements, which are connected, in this case, in the serial way, as one representing element, but it is only mathematical model, which I can apply to further calculation for, let's say, analysis task and synthesis task. It is easier to maintain, to use this aggregated model because it's only one formula, not the system of formula, as you can see on the left side, I mean just here. So it is the general idea, and you can see where from we just get this description. No to zapisz plik on optimization. Muszę zapisać to systems theory. Okay. To jest 10. Okay. Okay. So, coming back to the slide, to the presentation. You can see this presentation.
Yes, we can see it.
So, okay. So it is now clear where from we get this formula. Of course, we can just imagine how to derive the second one. And of course, we can derive this one. For example, we will do it on exercises. And it is very important the proper order of multiplication here, because in general it can be possible in this way. And this order is coming from the derivation procedure, and we will do it on the exercises. Okay. But now I would like to show you analytical procedure, general attempt in the case in which we deal with single input, single output elements. So this attempt, in which as a final step we apply Cramer's method of solution of systems of linear equations, is valid only for single input, single output system, none for multidimensional, in which the description in the form of matrix relation exists. Only for single input, single output systems. And for example, it would be as follows. Okay, teraz tak. Znowu whiteboard. No whiteboard, no whiteboard. Oh, paint. Czemu się nie chce załadować? Coś się ładuje? Nie.
Nie.
Coś mi się chyba...
Widzimy tylko Microsoft Teams.
Ale widzicie mnie?
Tak.
No, w okienku tak.
Panienka z okienka? Cholera, no to czekaj. Zobaczymy, może whiteboard się będzie coś odezwie. O, whiteboard się odezwał. Bo mi się nie chciała ta załadować jakby ta strona z Painta. Okay. Oh. And maybe next, maybe this. Aj, coś. Momencik. A, to już, znaczy jest mało czasu. Momencik. Maybe then this whiteboard. Widać ten whiteboard? You can see this whiteboard?
Yes.
There's a lack of time now. But I try to just formulate this problem and to show how to solve. For example, let do it for such structure. I mean this structure with feedback. Of course, negative one. Okay. And we deal with single input, single output system. It is very easy. And at the beginning, of course, it is very simple system. But I would like to show you the idea of this approach to this problem, which can be applied this approach to the very big problem. But of course, for me, it's easier to show you on this simple example. First of all, I should denote all signals in this scheme, in this figure. For example, I do not know what will be this system, so I denote it by W1. This signal is Y. Of course, here we also have the same signal because it's some kind of divider of signal, what means that in every point of this divider we have the same, exactly the same signal. So here, for example, we do not know what is the signal. Next, we will form an equation for every element in our system. In our system, we have three elements: two amplifier with amplification A and B, and this summing junction. No i teraz coś się skrzeniło, ktoś mi zabrał, że tak powiem, prawo głosu. Znaczy, some of you has taken from me the power, so I cannot just write anything on this table because I have no pen. Oh, okay, thank you. Just 1 minute, please. Nie wiem, co zniknęło, ktoś mi to coś cyknął, czy samo zniknęło. So we can write that Y is equal A multiplied by W1. W2 output of this element B, we can calculate according formula B multiplied by Y, and in this summing junction, summing point, we have such a relation that W1 is equal U subtract W2. Because this relation are for system with these connections, it means that we have system of equation. And in 2x time, dobrze będzie? No, maybe, poczekaj, nie, to będzie 18. In 2 weeks time, in 2 weeks time, because in a week we have holiday, Independence Day, and 2 weeks time we have meeting, and I will go on with this problem on this meeting. So I now export this obraz. On się zapisuje w pobranych. Okay. So for today is everything. If there are questions, so please, I will be present a few minutes later. And now thank you and see you in 2 weeks time and during exercises. So goodbye.
Goodbye.
Thank you.
Bye.
Thank you. Good.